Welcome to today's lecture on artificial intelligence. One logistical note for you is remember that next week we go back to Ingersoll 122. So you don't have to put up with these crazy tilted chairs here. And we appreciate those of you who have figured out how to put up with the crazy tilted chairs. Well, as you've seen so far in our conversation here, the last time we talked about neural networks, and neural networks are actually made up of lots of simple parts, which in our case we call the mathematical neurons, mathematical models of biological neurons. We arrange them into networks of layers that have hundreds or thousands of neurons in each layer and have lots of interconnections. And when you do that and train them, they can do some astonishing things, such as recognizing photos, interpreting speech, or translating languages. And as you probably noticed, to completely understand how these things work, you have to learn a lot of math, and that can be pretty daunting. So, although you don't have to learn the math, at least you can be comforted that the people who build these things know the math and that they have a solid mathematical basis on which they are building these neural networks. There is, however, a kind of major weakness which almost is so obvious that you don't notice it in these supervised learning networks, and that is obtaining the training data. Because the network needs training data to learn what it's supposed to do, and the quality of what it's able to do depends on the data that you have. These networks nowadays require, as you saw from Professor Oriskannen's lecture, massive amounts of data to train them. Where do these data come from? How do we get them? When you need massive amounts of data, remember, to train the network, if you have data that's like a million or 100 million photographs, every one of those photographs has to have a label with it telling you what the photograph is about. And then the objective is to show the photographs to the neural net and have it learn to tell you what each photograph is about. Well, somebody's got to label that to get this process going. Somebody has to do that. I saw a recent news story where there's actually a company that hires people part-time in Asia using the internet to employ them, and their job is to sit there for hour after hour looking at photos from a colonoscopy database, and they're supposed to draw red circles around red spots they see on the colon walls in those photographs. And then over a period of time, they amass quite a database of marked up colonoscopy pictures, which they then sell to medical device companies who try and build diagnostic systems that will recognize precancerous polyps. Well, when you read this story, at least I don't know how you would react. My reaction, there's something wrong with this picture here, that they're trying to build a system that would replicate a doctor, a trained physician, looking at colonoscopy photographs, and the thing is being trained off of amateurs who don't know a thing about colonoscopy. So it makes me wonder about the reliability of these kind of things that need massive amounts of data and you don't know where they're getting it from. So because of many stories like this, there's been a lot of researchers looking at ways, asking the question, is it possible to build machines that learn just from the data without having to have anybody label it ahead of time? And there are a number of very important cases which you'll hear about today. Professor Chris Darken is here to talk to you about unsupervised learning, meaning there's nobody telling it what it should learn. It learns from the data, it learns from itself. Among the things he'll talk about near the end is some of these amazing breakthroughs that were produced recently by the system called AlphaZero or AlphaGo that played the game of Go and beat the world Go master a couple of years ago. The most amazing thing to me about that was that the people who built that system, once they had built it, it took the system 13 days of training and playing simulated games until it was able to achieve a grandmaster level of play. And by comparison, it took 30 years for the people who are working on chess systems to build a chess machine, which is basically a rule-based machine, to beat the world grandmaster of chess. And chess is much easier than Go, according to all the experts. So this is pretty amazing that we can get a machine that can learn something really hard that fast. And Chris Darken, who's a member of our CS faculty and also a member of the MOVES faculty, will be talking to you about that today. Chris, please welcome him.
Okay, thank you, Peter. I hope you can all hear me all right. Let me see if I have a cursor. Oh, I do. Fantastic. Okay, good. So I'm going to talk about unsupervised learning. So here's kind of the whole talk up front here. The bottom line about supervised learning, it's a wonderful thing, but you don't always have the data, as Peter just alluded to. But it's amazing but true that in some situations you can solve the problem anyway. And these sets of techniques are what's referred to as unsupervised learning. And they often depend on using the exact same technology that you had talked about yesterday in some clever way, with some clever twist. So what I'm going to talk about briefly this afternoon is two of the most significant algorithms in this family. One is anomaly detection, and the other is deep reinforcement learning, which has been grabbing all the headlines lately. So I want to discuss what these algorithms do and try to at least make a decent start on giving you the main principle that makes them work. And we'll call it a day. All right, so first, this is not a talk on supervised learning. That was yesterday. So for today, I'm going to adopt a black box model of supervised learning that you'll see here, right? So that's my supervised learner, that black blob. Before learning, we might present it with some input. It's always a list of numbers, right? That's always what you present. You get an output at the bottom there, which is also a list of numbers, and what those mean and why you're doing it, that depends, that varies application by application. But you see it's got a switch on the side there, and if you pull that switch down, then we go into learning mode here, where the operation is different. So we present an input at the top, and then on the right, we present what we would like the system to have produced. Okay? So if you see, if that was what we desired the system to produce, that's a 1 followed by a 0. Do you see the big, there's the 1, there's the 0. That's what we wish, and we didn't get our wish. And you see, after training, we still don't have our wish, but can you see the situation has improved? All right, it's moved ever so slightly toward the output that we wanted, and if we weren't happy, we could continue training on this or related examples. Okay, so that's going to be our supervised learner for this talk. Okay, so part 1, anomaly detection. All right. So I want to talk here for a minute about what turns out to be the very first problem I ever worked on for the Navy. This was when I was in industry, which was the Hilo gearbox failure prediction problem. This was back in the mid-90s. Okay? So there's a problem that gearboxes that seemed to be good at maintenance time were going sour in the air, and this made helos fall out of the air, which is pretty uncomfortable. So we really would like to know when that's going to happen. And we were working for our work from the vibration spectrum of the gearbox. So a bunch of numbers that represented what kind of vibrations the gearbox was making, and the goal is to predict failure. Okay, so this is an unsupervised learning talk, but for a moment, let's consider solving the problem in a supervised manner. So this is theoretically possible, okay? So we could take, we could take healthy gearboxes like this one. We could gather their vibration spectra. We could train with my black box supervised learner, and we'd say, well, we want that first input to be high when we have a healthy gearbox. We could get a bunch of unhealthy ones. Same process, except in that case, we want the second output to be high, and that's how we'll know when the system is saying it's healthy or unhealthy, okay? And then when we're done, if we were successful, we can now produce a new spectrum from a gearbox we're concerned about. We look at the output, and we might look at those two numbers. The second one's higher, right? That's more like this output, so we might say, oh, I'm worried about that one. That one might fail. That would be the idea. Okay, so what's wrong with that? Well, you know, nothing's wrong with it in principle. Actually, supervised learning is wonderful. It would be my preferred method, except that for this particular case, for this Navy data, we were only finding out about bad gearboxes by having the helos fall out of the sky. So we really don't want to just sit on our hands and wait for enough helos to fall out of the sky, so we have data to follow this approach on this slide. Okay, so what could we do instead? We could possibly do unsupervised learning. All right, how does this work? So in principle, the idea is that we're going to try to solve the problem now based on a database of healthy gearboxes only, because that data is easy to come by, okay? Now, when we get a new record and you say, oh, I'm concerned about this vibration data, the idea would be that we would compare it to our known good data, and if it's similar, we'd say it's normal. Otherwise, we'd say it's anomalous, and that only means that we would get a human expert involved at this point. Anomalous doesn't mean bad, it just means different, okay? And a human would decide whether anomalous meant failing or not. So that kind of a system is called an anomaly detector. And the trick here is to find a good measure of similarity. There's all kinds of measures you can come up with, and as it turns out, sometimes the simple ones are great, but often they're not the best. And the one I want to talk about this morning is one of the more complicated ones, which uses a neural network called a neural autoencoder, and it's one of the most successful measures and what we used for this particular data ourselves. So how does this work? Okay, now this is going to sound a little bit strange here, so follow along with me. So this is how we train a neural autoencoder. Here it is in training mode. We present it with some data in training mode. See the lever's down, okay? And we say what we want out in this case is the exact same data we put in. All right, what nonsense is this? We have that data. Why do we want it? Okay, well, all right, so the story is that we don't just use any neural network here. We use one that's been kind of crippled in a certain way. So it's not capable of learning the identity function, right? That's the function that just take whatever you give me, I just give it right back to you. It actually can't learn that function, okay? So the result is that after training a neural network, it does better reproducing data that it's been trained on than on data that it's not been trained on. And that's really the whole story here, because now I can come with a new vibration spectrum. I put it in. I see how well it's reproduced. I don't know if this is well or poorly, okay? But we compare those two, the input and the output. If it was really close, we'd say, it's similar to the good vibration spectra. And if it's not so close, we get concerned. We call it anomalous. The human expert comes in and says, okay, better not fly that helo today, okay? That's the idea. That's the easy problem I'm going to talk about this morning. Now, on to the other one, okay? Reinforcement learning. Okay, so completely different domain. So reinforcement learning is a system for learning actions, for a system that's going to continuously interact with some kind of an environment. It could be a military environment, but it's going to be a peg jump puzzle for us this morning, because that's easier to draw on a slide. So you've all seen this kind of puzzle. The black circles are the pegs. The other ones are empty holes. There's some kind of goal state like you see down here, so we're trying to get all the pegs off the board and just end up with one at the apex of the triangle here. Every time you jump a peg, you remove one peg from the board. Okay, so for example, you can move this peg to here, taking this peg in the middle out. Okay, and also to make a action selection problem, we need to specify a reward structure. So what kind of actions do we actually want? So the system is going to try, the goal is going to be for the system to try to maximize long-term discounted reward. I'll explain a little about what that means, but not like the instantaneous reward. We're not just going to try to hit a home run in the next 5 minutes and then fail for the rest of our lives, right? That would be bad. That's clearly not good long-term reward. So in this case, we could say we could have a maximum reward for 1 if you achieve the goal state. He could have a reward, quote unquote, of -1 if you get stuck, right, in some state where you can't solve it, okay? That happens all the time. But if you notice, most states of the board are not ones that will get either a reward of +1 or -1. They get no reward at all, or represented as a 0 reward, okay? So the reward is the information we're providing to the system to make it act better, but it gets almost no information. You will have to take action after action, and then way late in the future finds out, oh, you failed. Well, why did I fail? Well, you must have done something wrong. Well, I just made 20 moves. Well, maybe one of them was bad. Maybe one of them was good. Maybe the bad one overruled the good. So this is that's what makes it, that sounds like a hard problem. It should, because it is a hard problem, and it's what we're trying to solve with a reinforcement learner. But of course, as humans or as animals solve this kind of problem all the time. All right. Lest I forget, we would rather, if you're going to solve this puzzle, we'd rather you solved it in 10 moves than in 100 moves. So we're going to reduce the reward by a fraction f each time. We'll just keep multiplying by factors of f to reduce your effective reward if you're slow. Okay? All right. All right. Now, as with the problem we talked about before, there's a supervised approach to this. It actually has a name in this case. It's called behavioral cloning. Okay? So let's consider trying to solve this problem in a supervised way. So we might do it by letting an expert actually play the game. And we train over here by representing the board state for the system and then telling it, okay, and here's what the expert says is the good action to do in that state. And we let the expert play for a while, okay? And we try to, hopefully we get a neural net that will then allow us to put in a board state, and it will predict its best reflection of what the expert would do in that state. Okay, what could be wrong with that? So it could be perfect, right? I mean, ideally, okay? But the problem is that a neural net for a complicated problem, maybe for my little toy problem you could do it, but for a real world problem, a neural net is never a perfect copy of an expert's behavior. Never. There's always going to be at least slight differences, right? And those slight differences build up. And the result over time is that this system here is going to be presented with board states that are problematic. They're terrible board states that an expert would never let himself get into, but the behavior cloned learner will get into. It won't know what to do in those states, and that will cause the system to fail eventually. So that's the kind of accepted critique of behavioral cloning and why we don't see many systems of this nature out there, though we do use the idea partially. Okay, so now for the unsupervised alternative, and that would be deep reinforcement learning, so-called, and deep really means kind of neural here. It has a neural network inside of it. Okay, so let's talk about this. So this will take a little bit of your attention to follow this passage, and after this, it's home. We're home clear, okay? So here's what we're going to do here. Here's the key idea. What we'd like to do is we'd like to use a neural network to represent this function. I didn't just name this function myself, this Q of AS. This is a holy object in AI, so this is a known thing, the Q function. What it's supposed to do is you give it an action that you're considering and the current state of the world, and it tells you how well you'll do, not just instantaneously, but over the long term with that action. Okay? That's the idea of the Q function. And the suggestion here is, let's use our supervised learner. We'll give it actions and states and try to learn the long-term reward. Okay? All right. So first of all, why would we want to do that? Well, because if we could do it, it would totally solve our problem. Right? So what I could do is, if I have a state like this one down here and 4 different actions, or actually, you can look and count how many different peg jumps you can make. There's just 4 different possibilities. Okay, those would be the actions. If I had the Q function, I could evaluate it for each one of those actions on the particular state. This is the state up here. I would get back a number, and that would tell me how well that that approach should do over the long term. So basically, if you look, here I have 3 negative numbers, 1 positive one. I'll take the positive one, thanks very much, right? You can always just take the best number that you get down there and know that your play is optimal. Okay, that sounds good, right? That should sound good, okay, all right? But how are we going to do that, all right? All right, how could you train such a neural net, right? So it seems like you probably need to tell it what the long-term reward is, and how do you actually know what that would be in any complicated setting? Okay, all right, well, it turns out there's a way around. So try to follow this. Let's assume we're in this state, and we just took some action, A1. That's that particular peg jump on the bottom. It doesn't matter what it is. Just for an example, okay? And we've received some reward, right? And after every action, I'll tell you received a reward. For this one, it's 0, because you didn't get to the goal, and you didn't get stuck either, okay? And that's typical. It's almost always 0, okay? So you got to some new state that looks like this, okay? Now, we'd like to know what Q, so could we get smarter? Right? If we have a system that's making moves like this, could we get smarter about what Q of A1, S1 actually is? Okay, and it turns out we actually, even though I couldn't tell you exactly what the value is, we know a little something about it. Okay, and what we know is that whatever the long-term reward is for taking that action in this state, it's related to the long-term reward that you would get by taking the best possible move in the next state. Now, how is it related? Well, because the long-term reward from this state is just the immediate reward that you receive plus the long-term reward out of the next state if you make the best possible move. So that's what this mathy-looking thing is trying to tell you right there, and nothing else. Okay? All right. Now, if these two things are supposed to be equal, then why not? I could take a neural net and train it using this as a target value. Now, it looks risky, and if you sit here and say, "Nah, I don't believe it," I don't blame you, because what's in this target value? What's in this information I'm telling the neural net to learn? The max over this exact same function that isn't very good. That's why I'm actually trying to learn it. Okay? But the other part of it, this short-term reward, is solid. That's absolutely solid. And it turns out that this approach, that is the standard reinforcement learning approach, and it actually does work over time. And it can take a while, but it does work over time. Okay, so the neural net typically will become more and more accurate, and that, in a nutshell, is what makes neural reinforcement learning work. Here we are in the training mode with our mathy expression, training up our Q function, and then when we actually play, we give it a state S that we're in. We say, hey, how about this action? It tells us how good it is, and we use that to guide our play, and we play optimally. Okay? Ideally. Okay, except in the real world with finite amounts of training, it's never optimal. Okay, so just to give you a little bit more of a kind of a warm and fuzzy about how this works, so this is an experiment we did in my lab. So we're simulationists, so this is a very simple ground combat model, and we're taking some red forces, that's these guys down here, okay, and they're going to learn under reinforcement learning, hopefully to attack these blue guys up here, okay? If you just turn the system on, so that's what I'm going to show right now, just like nothing up my sleeves. Okay, they know nothing, right? They really know nothing, all right? So what's going to happen is, I'll turn it back on, the video back on, and you'll see, basically, since they don't know what to do, they will make random moves just to try stuff, okay? And then you will see that basically what they're doing is fishing around looking for a reward, all right? Now, you all know what the red guys should do, right? The red guys can see the blue guys, but they don't have any idea what those blue guys are there. They really have no idea. How do they know? Maybe what I'm trying to train red to do is to dance in the middle of the screen. They could do that pretty easily without any training. Maybe I want them all to run south as fast as possible. Maybe half of them should run east and half should run west. How do they know what we want? Okay? They won't know. So they're just going to stumble around feeling their way until by chance they do something that we reward, okay? And then they're going to use that to start refining their neural net model, their Q function, which will let them pick good actions. Okay, now this takes a while, okay? Even with a simple, relatively simple problem like this, okay, you're going to see just to get them to stagger over and take a whack at a blue guy. I mean, there's an attempt, but if you notice, red dies, so they didn't get any reward there, okay? Won't take too much longer. Eventually, they will maybe kill a blue guy. Not that time. You see the system resets every so often, because sometimes they'll just wander off the map, which doesn't really facilitate learning. Okay, now this red guy gets lucky. Okay, that's the first indication that they had of what they're supposed to do. And it's not nearly enough, but it's something, okay? Now, I'm speeding up time here, right? So much more time elapses. If you watch over time, you might notice that their behavior will become less and less random until eventually, I think I'm just going to kind of speed up. Where are we? We're doing okay on time, but still. Well, I'm right about the right point anyway. You'll see in a minute it will kind of reach its apex. They're doing better. They're kind of drifting a little more toward the north than otherwise. And 10 more seconds, and I think we'll be at the end. Okay, so this is the end of the training, and here you see that the red guys actually seem to know what they're there for. Okay, I won't say anything more about it because I'm not super happy with how red is using their forces, but at least they know to go kill the blue guys. Okay, most of the time. Okay, but now here's an example where it's a combat model. It's random. That last blue guy is a lot tougher than he looks. He's killed all the red guys. The other red guy doesn't have a clue what to do at this point. Okay, he's not scared, but he just doesn't have a clue. All right, but that pretty rarely happens. Okay, mostly they at least learn to kill the blue guys. Okay, so. All right, so let's talk a little bit about some of the reinforcement learning examples that you might have heard about in the news. I'm partial to the work of this DeepMind unit, which is a company that was founded in England, bought by Google, now held by Alphabet, which is Google's parent company. There are other things around. If you're interested, just so I don't forget, there are some good results in poker that I'm not really going to mention here. If you're interested in poker, go looking for that work. But this is all stuff done by DeepMind. So let's start in 2015, this DQN system. So this thing, why might you be interested? It learned to play literally dozens of Atari 2600 games. Now, the Atari 2600 is not a state-of-the-art video game system, okay? It's a little old. This is what a screen looks like. This is the breakout game there. But for like 2/3 of the game, it was able to achieve superhuman performance. So that's kind of interesting. Not all by any means. Some it was just ridiculously bad at. So you can go read about that if you're interested. One of the things I like to point out was the way the thing learned how to play breakout. So I mean, I played this game plenty when I was a kid. I'm sure you have more than a few people who have played games of this. Okay. All right, and you know they kind of made a big fuss about this, but it was something the network learned that you all know if you played this game. So the best possible thing you can do is just not kind of try to kill. So basically, with the paddle, you're hitting the ball up. It's eliminating the bricks, right? You don't want to eliminate them row by row. What you want to do is make a little hole and get the ball to go up there, and it will get stuck up there, and it just bounces around like mad on top. You don't have to do anything in the bottom with the paddle. It just stays up there until it eats most of the bricks. Interestingly, the system was able to learn that. And unlike me, who has kind of pretty poor reflexes, it's the computer driving the system. So once it learns, it's pretty much able to laser focus and drill a nice sharp hole and get that thing up and wipe out those bricks in no time. That was the DQN system. Then, notice, it's just 1 year later. They're pretty productive over there in England. There was a system called AlphaGo. There is a documentary. How many of you have seen the AlphaGo documentary? Has anyone seen it? A couple people have. If you have Netflix, at least recently it was free on Netflix. Go look it up. Its production values are pretty good, if I say so myself. So it captures this whole saga of them trying to build this system to become a world-class Go player for the first time. Because Go has been, it's generally acknowledged to be a much more difficult game than chess, at least for the computer. Okay, and eventually they came up with this AlphaGo system that managed to beat Isidore, who is, there's no one unique Go champion, but he is one of a small handful of ultra elite players, and they beat him 4-1. So that was pretty impressive. What I'd like you to know about that series of games was there was a particular thing happened. The first game, actually AlphaGo won, but it was pretty run-of-the-mill. The second game, on move 37, the system made a move that was very interesting. It was very interesting because it was so terrible. All the human experts looking at it were scratching their heads. As a computer scientist, I would think, it's a bug, you know, even good systems have bugs sometimes. It just, you know, it took a powder, you know, there's no hope. And then it goes on to crush Isedal in the second game as well. So what was interesting there is, in retrospect, people realized that what looked like a terrible move, all humans agreed it was a terrible move, it was definitely not a terrible move. So it found some completely unique way of attacking. That should be pretty interesting if you're thinking of defense applications. AlphaZero system, the AlphaZero system came next in 2017-18, so not content to merely play Go, you can tell AlphaZero to learn chess or shogi or Go. And unlike the AlphaGo system, AlphaZero does not make use of any expert recorded play at all to ramp itself up. It learns entirely by playing itself. Last but maybe not least is the AlphaStar project, which is their ongoing work there. You can look online if you want to see about that. There are really no good publications yet, okay? But they have shown that they were able to beat a professional quality StarCraft player. So StarCraft is a video game, but it's a far cry from Breakout. So it's very much more, very akin, in my mind, to a constructive simulation of the kind we use all the time. And so, it will be very interesting to see where that goes. I guess they're waiting to totally perfect it before publishing that work, so watch for that. All right, so I'm almost done. Just a couple comments on things I think are interesting. Want to make sure I call these things out. Okay, so one thing is that just being very superficial about it, the information for some of these systems, think of the Atari system. We're presenting this system with a screen of information, literally like the information right on the screen that a human sees. We're asking it to make button presses in response, okay? Just on an input-output level, like how many military jobs could that possibly look like? A lot, okay? Now, it doesn't mean it would succeed at those jobs, but at least input-output-wise, you could plug it in and try, if you're brave. Okay. Look at the flexibility of the system. So it learned dozens of video games. One system can learn chess or shogi or Go. Okay, well that's kind of interesting. So maybe how far can it extend in our direction for tasks we might care about? The performance is clearly superhuman in many cases, so that's pretty interesting. And the tactics that surprise all human experts. Okay, like we're going to have a computer that can generate completely novel tactics. Please, let's let our coalition have it rather than the opposing coalition. So that's pretty interesting. Now, all those results are great, but this is very much still a research project. There are lots of issues that I think most people would acknowledge, like how you actually capture the state of the system to present to your learner can be difficult, and there's various efforts involved to try to make that easier. The reliability, not of a trained system, I mean, I'm not critiquing AlphaGo, but just once you have a decent system, and you press the button to learn, you will find that there are dozens of different algorithm variants you could use. Each of those algorithms has dozens of parameters that you have to set, and those are consequential parameters. If you set them wrong, sometimes even just a little wrong, it doesn't work, okay? And last but not least, these systems don't just learn quickly. They can play quickly once they've learned, but to get them to learn usually takes at least hours on a computer for a real thing, not like my little demo, but to learn Go or to learn something like that, hours or days on a fast computer, and you might need many runs to make it work. So that's what I had in mind to say, but I'll stand to questions if there are any.